Chromatography is a laboratory technique used to separate and analyze the components of a mixture. The separation is based on the differential affinities of the compounds for two phases, a stationary phase and a mobile phase. The stationary phase is a solid or a liquid supported on a solid, and the mobile phase is a liquid or a gas that moves through the stationary phase. As the mobile phase moves, different compounds in the mixture travel at different speeds, causing them to separate. Chromatography is widely used in chemistry, biology, and medicine for purposes such as purifying substances, analyzing complex mixtures, and identifying unknown compounds. Planar chromatography is a subset of chromatography in which the stationary phase is present on a flat plane or surface. The two main types of planar chromatography are paper chromatography and thin layer chromatography, TLC. In these techniques, the stationary phase is spread out in a thin layer on a flat surface, such as a glass plate, aluminum foil, or paper. The sample to be analyzed is applied as a small spot or line near one edge of the surface, and the mobile phase moves across the surface by capillary action or gravity, causing the components to separate.
Greetings everyone. For this topic, we choose thin layer chromatography. What is thin layer chromatography? It is a type of adsorption chromatography that is used to separate, identify, and quantify components in a mixture. It is a form of planar chromatography where the stationary phase is a thin layer of adsorbent material that are coated on a flat substrate such as glass plate. The glass plate will be coated with solid absorbent such as silica gel, along with the mobile phase that is liquid volatile solvent. Thin layer chromatography consists of three components, which is stationary phase, mobile phase, and sample application. For the stationary phase, this TLC is a thin layer of adsorbent material such as silica gel, alumina, or cellulose. This layer is coated onto a flat with inert support like glass, plastic, or aluminum plate. Silica gel is the most commonly used adsorbent due to its effectiveness in separating a wide range of compounds. Mobile phase. It is a mixture of solvent that moves through the stationary phase by capillary action. It is crucial to choose a proper solvent. Depends on the nature of the sample components. You can use methanol, ethyl acetate, toluene, and chloroform. The sample application will proceed by applying a small spot or streaks near the base of the TLC plate by using a capillary tube or a micropipette. Ensure to apply it accurately and precisely for reproducible results. There are 6 procedures involved by handling thin layer chromatography. Firstly, preparing and activating the TLC plates. The plates were pre-coated with a layer of adsorbent material like silica gel, alumina, or cellulose. The plates are ensured to free from the contaminants by handling them with clean gloves and using forceps to avoid the contact on the adsorbent layer. Some TLC plates require to be heated in oven for about 110 and 120 degrees for about half an hour. This is to remove any moisture and enhance the adsorbent's activity. After the activation, let the plates to cool in desiccator to prevent moisture absorption from the air. Secondly, to spotting the TLC plate with sample. To prepare a sample, you need to dissolve a small amount of the sample in a proper solvent to make a concentrated solution. To spotting, by using a capillary tube or a micropipette, apply a small spots of the sample solution near the bottom edge of the plate. Make sure it's about 1 to 2 cm from the edge. Make sure the spots are small and concentrated to achieve a great solution. Ensure there are no overlapping spots if you attach a multiple sample on the same plate. Allow the spot to dry completely before proceeding to the next step. Third, developing the TLC plates. It consists of chamber, plate, and solvent form. First, adding a small amount of the mobile phase, which is solvent, at the bottom of the chamber. Make sure the solvent is below the level of the sample spots to prevent dissolving. A common solvent that can be used is methanol, ethyl acetate, toluene, and chloroform. It depends on the sample's nature and the desired separation. Next, place the spotted plate in the development chamber upright with the spotted end down, and then seal the chamber to ensure a saturated atmosphere. It helps to give a consistent solvent migration. Allow the solvent to ascend the plate by capillary action until it reaches an appropriate head, usually at about 2 or 3 of the plate's head. Ensure there's no solvent front reach the top edge of the plate. Next, remove the plate from the chamber and immediately mark the solvent front. Mark the highest point reached by the solvent with a pencil, not a pen. Next, drying the plates. Let the TLC plate dry completely in a well-ventilated area or even under a stream of warm air. This is to ensure the solvent evaporates and leaving the separated components on the plate. Meanwhile, visualizing the substance spots. There are 3 techniques, which is UV light, iodine staining, or even chemical reagents. Most of compounds is fluoresce under UV light, so we can just place the TLC plate under UV lamp to observe and mark the spot. For iodine staining, expose the plate to iodine vapor in a sealed chamber. The iodine reacts with many organic compounds that it produces a brown spot. For the chemical reagent, spray the plate with a specific chemical reagent that react with the compounds to form colored spot. For example, you can use anhydride reagent for amino acid or sulfuric acid for jarring. Finally, after separating session, we need to measure it to precise observation. We need to measure the distance traveled by each substance spot from the original baseline, that is the center of the spot. Measure the distance by the solvent from the baseline by using the retention factor formula, which is distance traveled by the compound divided by distance traveled by the solvent front. Gather all the information and solve it. Retention factor values are unique for each compound under any specific condition, since it helps in identifying substances by comparing with known standards.
There are 3 applications of TLC in herbal industry. First is quality control. TLC ensures the consistency and consistency of herbal products by verifying the presence and concentrations of active compounds. This is vital for maintaining the therapeutic efficacy and safety of herbal medicines. For example, in the quality control of ginkgo biloba products, TLC is used to check for the presence of specific active compounds, such as flavonoids and terpenoids. These compounds are responsible for the therapeutic effects of ginkgo biloba. Next is detection of adulterants. Adulterants in herbal products can compromise their safe tightness. TLC helps in detecting adulterants and contaminants, ensuring that the products are pure and safe for consumption. For example, TLC helps detect adulterants in potency root products. By developing a TLC plate with a sample and comparing it to known standards, adulterants like others berberine containing plants can be identified. These ensure that consumers receive pure and ineffective products without their harmful and ineffective substitute. And lastly, chemotaxonomy. Chemotaxonomy involves classifying the plants based on their chemical profiles. TLC is used to separate and identify chemical constituents of plant extracts. The resulting patterns of spots, chemical fingerprints, can distinguish between different species. For example, TLC is used to identify psychoactive plants by spotting plants extract on the TLC plates, developing them in a solvent, and visualizing the spots. The patterns are compared to those of non-psychoactive compounds. Another example is TLC plates can detect alkaloids in plants like peyote and ayahuasca, which are known for their hallucinogenic properties. The presence of these alkaloids is confirmed by matching the spots or values with those of standard alkaloids. What are the advantages of TLC? First is ease of use. TLC is straightforward and easy to perform, requiring minimal training and basic laboratory equipment. Second, cost effectiveness. The materials and equipment required for TLC are relatively inexpensive compared to the other chromatographic techniques such as HPLC. And lastly, sample application. TLC provides quick results, often within minutes to an hour. This speed is advantageous for rapid screening of raw materials and finished products, enabling timely decision making in quality control processes. TLC has its own benefits. It also comes with its own limitations. First is low sensitivity. TLC generally has low sensitivity compared to techniques like high-performance liquid chromatography. Next, TLC can suffer from reversibility issues due to variations in plate preparations, solvent compositions, and environmental conditions. And lastly, quantitative limitation. While TLC is excellent for qualitative analysis, its quantitative capabilities are limited. Accurate quantifications of compounds require more advanced techniques like HPLC, which can precisely measure concentration level. To conclude, TLC is a vital and versatile tool in the herbal industry, essential for quality control, detecting allergens, and classifying plant species. Its simplicity, cost-effectiveness, and rapid result make it ideal for routine analysis. While it has its own limitations in sensitivity and reproducibility, TLC advantages ensure the production of high quality, safe, and effective herbal products. By leveraging TLC, the herbal industry can maintain the integrity and efficacy of its offering, contributing to the advancement and reliability of herbal medicine. Thanks for watching. These are the references used for this video.